Look at this giant spaceship pointing toward deep space. It looks powerful, ready to travel anywhere in the universe. Our galaxy, the Milky Way, has more than 100 billion stars scattered across a space so big that light takes 100,000 years to cross from one side to the other. It seems like with enough technology, we could build even bigger and faster ships to explore every corner of it. But here's the truth that changes everything. There is a place in our own galaxy that no human spaceship will ever be able to reach, no matter how advanced our technology becomes. The center of the Milky Way, that bright heart filled with millions of crowded stars, hides forces so extreme and so violent that they would destroy anything that tried to get close. Get ready to relax and fall asleep while we explore why this dream of reaching the heart of our galaxy will forever remain just a dream. How can there be a place in the universe that is close to us, but at the same time completely impossible to visit? Subscribe to the channel. Leave your like and comment what part of the world you're watching from. Get comfortable and relax. Let's begin. Have you ever looked up at the night sky and wondered what lies at the heart of our galaxy? While this curiosity is natural, the harsh reality is that humans will likely never witness the galactic center firsthand. The most fundamental obstacle preventing us from exploring the center of our galaxy is simply the unfathomable distance that separates us from it. The galactic center sits approximately 26,000 light-years away from Earth. To put this in perspective, this means that the light we currently observe from the galactic center actually left its source 26,000 years ago, when humans were still painting on cave walls and mammoths roamed the Earth. This distance is so vast that it defies human comprehension in practical terms. Even if we could somehow travel at the speed of light, which physics tells us is impossible for any object with mass, the journey would still take 26,000 years. Our current fastest spacecraft, like Voyager 1, are travelling at speeds of around 38,000 miles per hour. While this seems incredibly fast by terrestrial standards, it's merely crawling by cosmic measures. At such velocities, a spacecraft would take more than 500 million years to reach the galactic center. The magnitude of this time frame exceeds not just any conceivable mission duration, but dwarfs the entire span of human civilization. Modern humans have only existed for about 200,000 years, and our recorded history covers barely 6,000 years. The voyage would take longer than humans have existed as a species. To visualize this distance another way, consider that light, the fastest thing in the universe, takes a little over 8 minutes to reach us from the Sun. It takes 4 years to reach us from the nearest star beyond our solar system. But from the galactic center, 26,000 years. The light we see from there now began its journey when our ancestors were living in the Stone Age. This extreme distance creates problems beyond just travel time. The space between our solar system and the galactic center isn't empty. It's filled with interstellar dust, radiation, stars, nebulae, and countless other objects and hazards. Navigating this vast expanse safely would require precision and technologies far beyond our current capabilities. When astronomers study the galactic center today, they're not looking at it as it currently exists, but rather as it was 26,000 years ago. This time delay means that any information we have about potential destinations near the galactic center is already outdated by millennia, making detailed mission planning essentially impossible. Even communication becomes an insurmountable challenge across such distances. Any radio signal or transmission would take 26,000 years to reach Earth from a spacecraft at the galactic center. This means that mission control would be completely out of touch with any expedition, with no practical way to provide guidance, updates, or assistance. The sheer scale of our galaxy also means that we've only mapped a tiny fraction of what lies between us and its center. Most of the stars, planets, and other phenomena in this vast region remain unknown to us. Any journey would be venturing into largely uncharted territory for the majority of its duration. For comparison, consider that humanity has only recently managed to send spacecraft out of our solar system, a journey measuring mere light hours. The challenge of the galactic center is not just quantitatively greater, it's qualitatively different, representing a leap from neighborhood exploration to crossing an ocean thousands of miles wide with a rowboat. Some optimists suggest that future generations might develop technologies allowing for suspended animation or multi-generational ships, where entire communities would live and die during the journey, with only distant descendants reaching the destination. But even these concepts face enormous practical challenges. The engineering requirements for a vessel that could operate autonomously or support human life for thousands of years, let alone tens of thousands, are beyond anything we can currently design or maintain. The vast interstellar distances also create propulsion challenges that go beyond just the time required. The energy needed to accelerate a human-carrying spacecraft to even a small fraction of the speed of light would be astronomical, requiring fuel reserves far greater than anything we could practically carry. Interstellar distances also mean that any mission would have virtually no margin for error. A minor course deviation early in the journey would result in missing the target by potentially trillions of miles. Navigation would need to be perfect over timescales where the positions of stars themselves change significantly. Scientists continue to study the galactic center through telescopes and other remote sensing equipment, gradually building our understanding of this mysterious region. But the reality is that the distance barrier represents a practical limit to human exploration that may never be overcome. Our understanding of the galactic center will likely always come from remote observation rather than direct visitation. The distance to the galactic center isn't just a challenge of engineering or technology, it represents a fundamental limitation imposed by the scale of our galaxy and the finite nature of human lifespans. While science fiction may envision workarounds to these limitations, the practical reality is that 26,000 light-years may forever remain an uncrossable gulf for physical human exploration. Limitations of current and theoretical propulsion. When discussing space travel to distant regions like the galactic center, the conversation inevitably turns to propulsion systems. The cold reality is that both our current propulsion technologies and even theoretical future systems face fundamental limitations that make such journeys practically impossible. The challenge isn't just about building a faster engine, it's about confronting the basic physics that govern how we move through space. The most advanced propulsion systems we currently possess can achieve speeds that, while impressive on a planetary scale, are utterly inadequate for galactic travel. The New Horizons spacecraft, one of humanity's fastest, travels at roughly 36,000 miles per hour. At this speed, reaching the galactic center would take approximately 700 million years, more than 150 times longer than dinosaurs have been extinct. Chemical rockets, which power all current human space exploration, are fundamentally limited by the energy contained in chemical bonds. Even the most efficient chemical reactions release relatively small amounts of energy per unit mass. This creates an insurmountable problem. To go faster, you need more fuel. But more fuel means more mass, which then requires even more fuel to accelerate. This vicious cycle, known as the rocket equation tyranny, puts a practical ceiling on the velocities achievable with chemical propulsion. More advanced concepts like nuclear propulsion using fission or theoretical fusion rockets offer significant improvements but still fall far short of what would be needed. A nuclear pulse propulsion concept like Project Orion might achieve speeds of perhaps 8 to 10% of the speed of light under ideal circumstances. Even at such velocities, the journey to the galactic center would take over 260,000 years. Ion drives and other electric propulsion systems offer excellent efficiency but very low thrust. While they can eventually reach higher speeds than chemical rockets, they do so over such long acceleration periods that they're impractical for missions requiring human crews. Some scientists have proposed more exotic theoretical propulsion methods, such as antimatter engines. Antimatter annihilation releases energy with 100% mass-energy conversion efficiency, far better than chemical or nuclear reactions. However, the production challenges are staggering. With current technology, producing just 1 gram of antimatter would take longer than the age of the universe and cost more than the entire global economy. Even with theoretical future production improvements, the containment challenges for significant quantities of antimatter may prove insurmountable. Solar sails and related concepts like laser-pushed light sails have been suggested as fuel-free alternatives. These systems use radiation pressure from the sun or lasers to generate thrust. While promising for interplanetary travel, they suffer from rapid power drop-off with distance. Beyond our solar system, a solar sail would receive negligible radiation pressure, making it ineffective for interstellar journeys. Perhaps the most famous theoretical propulsion concept is the warp drive, popularized by science fiction. Serious scientific investigation of this idea, particularly the Alcubierre drive concept, reveals profound challenges. Such a system would require exotic materials with negative energy density, something that has never been observed and may be fundamentally impossible according to known physics. Even if possible, the energy requirements would be astronomical, possibly requiring more energy than exists in the observable universe. Another theoretical concept, the Bussard ramjet, proposes collecting hydrogen from interstellar space as fuel. While elegant in theory, the practical challenges of creating an electromagnetic scoop large enough to collect sufficient fuel, while dealing with drag and radiation from ionized particles, make this concept problematic for actual implementation. Gravity assists, which spacecraft routinely use for interplanetary travel, offer no practical benefit for galactic center journeys. The distances between stars are simply too vast for this technique to provide meaningful acceleration. The fundamental issue with all propulsion concepts for reaching the galactic center is the relationship between mass, energy, and acceleration. Einstein's famous equation, E equals mc squared, defines the ultimate conversion of mass to energy. Even with 100% efficient conversion, which antimatter approaches, the fuel requirements for accelerating a vessel large enough to support human life to even a modest fraction of light speed would be prohibitive. Consider a spacecraft with the minimal mass needed to support a small human crew, perhaps 1,000 tons. Accelerating this mass to just 10% of light speed would require energy equivalent to the world's total energy production for several years, even with perfect efficiency. And this calculation doesn't include the fuel needed to decelerate at the destination or navigate during the journey. Some have suggested nuclear pulse propulsion using thousands of nuclear bombs detonated behind a pusher plate to propel a spacecraft. While theoretically capable of reaching perhaps 4 to 5% of light speed, the engineering challenges of building a structure that could withstand thousands of nuclear detonations while protecting a human crew are immense. Even at such speeds, the journey would still take over 500,000 years. The reality is that the physics of propulsion creates a practically insurmountable barrier to human travel to the galactic center. While unmanned probes with very low mass might someday be accelerated to higher velocities, vessels capable of supporting human life face fundamental limitations based on the relationship between mass, energy, and velocity. Even theoretical breakthroughs in physics that might allow for circumventing these limitations, like stable wormholes or space-time manipulation, face enormous challenges in terms of energy requirements and the need for exotic forms of matter that may not exist. For the foreseeable future, and perhaps indefinitely, human exploration of the galactic center will remain in the realm of science fiction rather than practical possibility. The limitations of propulsion technology, both current and theoretical, represent a barrier that may prove as impassable as the vast distance itself. Beyond the challenges of distance and propulsion, the human element itself presents perhaps the most profound barrier to exploration of our galaxy's center. Even if we could somehow develop spacecraft capable of travelling at significant fractions of the speed of light, we would still face an inescapable biological reality. The human lifespan is simply incompatible with the timescales required for such voyages. The average human lifespan today is approximately 70 to 80 years, even with optimistic projections of medical advancements. It's difficult to imagine extending human life beyond 150 or 200 years in the foreseeable future. Now compare this to the tens of thousands of years required for a journey to the galactic centre, even using theoretical propulsion systems far beyond our current capabilities. The mismatch is stark and unavoidable. This fundamental incompatibility means that any mission to the galactic centre would necessarily be a multi-generational endeavour. The original crew who departed Earth would never see the destination. Their children, grandchildren, and dozens of generations of descendants would live and die aboard the spacecraft before it ever approached the galactic centre. The people who finally arrived would have no personal connection to Earth or the original mission parameters. They would be, in essence, a different civilization entirely. The challenges of maintaining a viable human population aboard a spacecraft for thousands of years are immense and largely unaddressed by current space mission planning. For genetic health, population experts suggest a minimum breeding population of at least 2,000 individuals to maintain sufficient genetic diversity and avoid the dangers of inbreeding over multiple generations. This number already makes spacecraft design exponentially more challenging in terms of size, resource requirements, and life support capabilities. Even with a sufficient initial population, genetic drift over thousands of years would inevitably occur. The humans who arrived at the galactic centre would likely be genetically distinct from those who remained on Earth, having evolved under the selection pressures of their closed spacecraft environment for hundreds of generations. Whether they could even be considered the same species as the humans who launched the mission is debatable. The social and cultural challenges of a generational ship are equally daunting. How would you maintain mission focus and purpose among people who have never known any world but the interior of a spacecraft? What kind of governance system could remain stable for thousands of years? History shows that human societies undergo major transformations over much shorter time spans. Religious, political, and social revolutions could easily derail the mission's original purpose. Education and knowledge preservation would be critical, but extremely challenging. The ship would need to maintain and transmit not just the technical knowledge needed to operate and repair its systems, but also the scientific understanding necessary to conduct meaningful research upon arrival. Over thousands of years, language itself would likely evolve, potentially making original technical documents incomprehensible without specialized training. The psychological aspects of generation ships present another layer of complexity. Humans evolved in open environments with horizons, changing seasons, diverse ecosystems, and day-night cycles. The psychological effects of being born, living, and dying within the confines of a spacecraft, never feeling natural gravity, never seeing an unfiltered sky, never experiencing weather or seasons, are unknown but potentially severe. Studies of isolated communities on Earth suggest that such conditions could lead to widespread depression, anxiety, and social dysfunction. Ethical questions also emerge about the consent of future generations. The original crew might volunteer for such a mission, but their descendants would have no choice in their participation. They would inherit a life aboard a spacecraft and a mission they never agreed to undertake. This raises profound moral concerns about the right to determine one's own destiny versus being born into predetermined roles in a mission planned centuries earlier. Resource sustainability presents yet another challenge. Any generation ship would need to establish a completely closed ecosystem that could function without external inputs for thousands of years. Our most advanced closed ecosystem experiments on Earth, such as Biosphere 2, have failed after just a few years. Creating truly sustainable life support systems that could function autonomously for millennia exceeds our current understanding of ecology and environmental engineering. The medical challenges are similarly daunting. A generation ship would need to maintain advanced medical capabilities for thousands of years without external support. New diseases might emerge in the closed environment, while the crew's immune systems might weaken without exposure to the diverse pathogens found on Earth. Addressing these challenges would require maintaining sophisticated medical knowledge and equipment over countless generations. Social cohesion over such timescales presents perhaps the most unpredictable variable. Historical examples suggest that human societies frequently fracture along ideological, religious, or cultural lines over much shorter periods than would be required for a journey to the galactic center. Internal conflicts or civil war aboard a generation ship could be catastrophic, potentially ending the mission entirely. The knowledge that one will never personally see the mission's completion could also affect motivation and decision-making. Humans generally act differently when they can expect to see the consequences of their actions within their lifetimes. Maintaining dedication to a goal that will only be achieved by distant descendants requires a level of altruism and long-term thinking that has rarely been demonstrated in human history. All these human factors combine to form a barrier that may be even more insurmountable than the physical challenges of distance and propulsion. Our biology, psychology, and social structures have evolved for life on Earth's surface over relatively short time spans. The requirements for galactic center exploration exist in direct opposition to these fundamental aspects of human nature and capability, adding to the already formidable challenges of distance, propulsion, and human lifespan is another deadly obstacle: the intense radiation that permeates interstellar space. This invisible barrier represents one of the most serious threats to any potential mission to the galactic center, and our current shielding technologies are woefully inadequate to address it over the timeframes required for such a journey. Space is not the empty vacuum many imagine it to be. It's filled with various forms of radiation, from solar wind particles to cosmic rays, high-energy particles that originate from distant supernovae and other energetic cosmic events. These particles travel at nearly the speed of light and carry enough energy to penetrate spacecraft hulls and damage both electronic systems and biological tissue. On Earth, we're protected from this cosmic radiation by our planet's magnetic field and atmosphere. Even astronauts in low Earth orbit receive some protection from these natural shields. But a spacecraft heading to the galactic center would have to provide its own radiation protection for thousands of years, a challenge far beyond our current technological capabilities. The health effects of long-term radiation exposure are severe and cumulative. Cosmic radiation damages DNA, increasing cancer risk and potentially causing mutations that would be passed down to future generations. Studies of astronauts who spent months on the International Space Station already show concerning changes at the cellular level. Now imagine exposure not for months but for thousands of years across multiple generations. The intensity of cosmic radiation isn't constant throughout the galaxy either. As a spacecraft approached the galactic center, radiation levels would increase dramatically. The center of our galaxy contains millions of stars packed into a relatively small volume, along with the supermassive black hole Sagittarius A star. The combined radiation output of these objects creates an environment far more hazardous than the relatively quiet neighborhood of our solar system. Current spacecraft use various forms of passive shielding against radiation, typically layers of aluminum or other materials that can block some incoming particles. But these systems face a fundamental limitation. Effective radiation shielding requires mass, and more mass means more fuel required for propulsion, creating another vicious cycle that makes the mission increasingly impractical. For a journey to the galactic center, the shielding would need to remain effective for thousands of years without degradation. All known materials suffer radiation damage over time, meaning that the shielding itself would gradually become less effective as the journey progressed. This would happen precisely when protection becomes most critical as the ship approaches the more radiation-intense regions near the galactic center. Active shielding technologies, such as electromagnetic fields that could deflect charged particles, offer a theoretical alternative to massive physical barriers. However, generating fields strong enough to provide meaningful protection would require enormous energy inputs sustained over thousands of years. The engineering challenges of maintaining such systems for multiple millennia far exceed our current technological horizon. The radiation problem extends beyond human health to affect virtually all aspects of a potential mission. Electronic systems, crucial for navigation, life support, and communication, are particularly vulnerable to radiation damage. High-energy particles can cause bit flips in computer memory or damage semiconductor junctions in processors and sensors. Over time, this radiation damage accumulates, causing increasingly frequent system failures. Modern spacecraft use radiation-hardened electronics that can withstand much higher radiation doses than consumer electronics. However, even these specialized components have finite lifespans when exposed to continuous radiation. For a journey of thousands of years, electronic systems would need to be either completely self-healing or designed with redundancies and replacement capabilities far beyond current engineering practices. The biological effects of multi-generational radiation exposure introduce another layer of uncertainty. Beyond the immediate health risks of cancer and radiation sickness, there are concerns about subtle genetic damage accumulating over generations. Natural selection within the closed environment of a generation ship might eventually produce humans with greater radiation resistance, but this process would likely involve significant suffering among earlier generations and could lead to genetic divergence from Earth humans. The region surrounding the galactic center presents even more extreme radiation challenges. It contains numerous neutron stars, stellar mass black holes, and regions of intense star formation, all of which generate various forms of deadly radiation. X-rays and gamma rays from these sources would penetrate most conventional shielding materials, creating an increasingly hostile environment as the ship approached its destination. Near the supermassive black hole at the galaxy's center, radiation levels would reach extremes that no known shielding technology could counteract. The accretion disk surrounding Sagittarius A star emits intense radiation across the electromagnetic spectrum. Any spacecraft attempting close observation would face radiation levels thousands of times higher than what would be immediately lethal to humans. Water is often suggested as an effective radiation shield due to its hydrogen content and molecular structure. A theoretical generation ship might use its water reservoirs as shielding, essentially surrounding the crew compartments with the water needed for the journey. However, even this approach would require enormous quantities of water to provide adequate protection, again increasing the vessel's mass beyond practical limits for propulsion. Some speculative approaches involve using the ice and material found in comets and asteroids as raw materials for continuous shield replacement during the journey. However, the technical challenges of mining, processing, and fabricating new shielding components while in deep space exceed our current engineering capabilities by orders of magnitude. The combination of continuous exposure, increasing intensity near the destination, and the degradation of shielding materials over time creates a radiation barrier that may ultimately prove as impassable as the distance itself. Our biology remains fundamentally incompatible with the radiation environment of deep space over the timescales required for galactic center exploration. The radiation hazards of deep space travel become dramatically more intense as we approach what might be the most dangerous object in our galaxy, Sagittarius A star, the supermassive black hole lurking at the Milky Way's center. This cosmic monster isn't just another obstacle. It represents a fundamentally hostile environment that defies human exploration in ways that make even interstellar radiation seem manageable by comparison. Sagittarius A star possesses a mass approximately 4 million times greater than our Sun, compressed into a space that's astronomically compact. This concentration of mass creates gravitational forces so intense that they warp the very fabric of space-time around the black hole. Any spacecraft approaching this region would experience these gravitational distortions in ways that our current engineering cannot possibly accommodate. The immense gravitational pull of Sagittarius A star creates what scientists call tidal forces, differential gravitational effects that become stronger as objects get closer to the black hole. These forces don't just affect spacecraft navigation. They would literally stretch and compress any physical object approaching the black hole. A spacecraft venturing too close would experience these tidal forces as physical stress on its structure, potentially tearing it apart in a process astronomers grimly refer to as spaghettification. While Hollywood depicts black holes as cosmic vacuum cleaners that suck in everything around them, the reality is both more complex and more dangerous. Surrounding Sagittarius, a star is an accretion disk, a swirling mass of superheated gas and dust spiraling into the black hole. This material reaches temperatures of millions of degrees as gravitational energy converts to heat through friction. The resulting radiation output spans the electromagnetic spectrum, bombarding the surrounding space with lethal X-rays and gamma rays. The radiation environment near Sagittarius A star makes even the harshest radiation conditions in interstellar space seem mild by comparison. A spacecraft entering this region would be subjected to radiation levels thousands of times beyond what would be immediately lethal to humans, regardless of shielding technology. Electronic systems would fail rapidly as radiation overwhelms even the most hardened components. Making matters worse, the black hole generates powerful magnetic fields that interact with the charged particles in the accretion disk. These interactions create jets of particles accelerated to nearly the speed of light, shooting outward from the poles of the black hole. Any spacecraft in the path of these jets would be instantly destroyed by this concentrated stream of high-energy particles. The environment around Sagittarius A star is also highly unpredictable. Astronomers have observed flares of X-ray and radio emission as the black hole consumes larger chunks of matter. These flares represent sudden, dramatic increases in radiation output that could occur without warning during an exploration mission, overwhelming any protective measures in place. As if these dangers weren't enough, the region surrounding Sagittarius A star contains an unusually high concentration of stars, many of them older. Evolved stars that have expanded into their red giant phases or become unstable. This stellar density increases the risk of encountering stellar winds, radiation from nearby stars, or even stellar remnants like neutron stars that generate their own intense radiation fields. The time dilation effects predicted by Einstein's theory of relativity become significant near such a massive object. A spacecraft approaching Sagittarius A star would experience time passing at a different rate than observers farther away. This would create enormous navigational challenges and communication difficulties, as time itself would flow differently for the spacecraft compared to mission control. These relativistic effects would make coordinated maneuvers nearly impossible and complicate even basic operations. Even before reaching the extreme environment immediately surrounding the black hole, a spacecraft would encounter the so-called nuclear star cluster, the densest known star cluster in our galaxy. This region contains thousands of stars packed into a volume just a few light years across. Navigating through this stellar traffic jam while avoiding dangerous close encounters with stars and their radiation fields presents challenges far beyond our current capabilities. The nature of black holes creates another fundamental problem for exploration. We cannot directly observe what happens beyond the event horizon, the boundary beyond which nothing, not even light, can escape. This means any probe sent to study Sagittarius A star up close could never transmit data back once it crossed this threshold. Our understanding of the black hole's most interesting features would remain theoretical, as direct observation is physically impossible. The combination of extreme gravity, intense radiation, unpredictable flares, time dilation effects, and the fundamental information barrier of the event horizon creates an environment that is not merely challenging but fundamentally hostile to exploration with any technology we can currently envision. These conditions exist not due to engineering limitations that might be overcome, but because of the basic laws of physics that govern black holes and their environments. Scientists continue to study Sagittarius A star through telescopes and other remote sensing equipment, gradually building our understanding of this mysterious object. But the reality is that the extreme nature of supermassive black holes likely places them permanently beyond the reach of direct human exploration. The center of our galaxy, dominated by this cosmic monster, may remain forever observed but never visited. Even if by some revolutionary technological advance we could overcome the dangers posed by Sagittarius A star and the extreme radiation environment near the galactic center, we would still face a seemingly mundane but equally insurmountable challenge: sustaining human life for the duration of such a journey. This aspect of deep space exploration often receives less attention than propulsion or radiation shielding, but it represents a fundamental barrier that may prove impossible to overcome. Any spacecraft traveling to the galactic center would need to function as a completely self-contained ecosystem for thousands of years, a feat far beyond our current capabilities in life support and resource management. The longest humans have continuously lived in space is just over 14 months aboard the International Space Station, with constant resupply missions from Earth. A generation ship would need to function autonomously for thousands of times longer without any external support. The most basic human needs, air, water, and food, present enormous challenges for long-duration spaceflight. While the International Space Station recycles approximately 90% of its water supply, that still leaves a critical 10% that must be regularly replenished from Earth. Over thousands of years, even small inefficiencies in recycling systems would deplete critical resources. Oxygen regeneration presents similar challenges. Current space station systems split water molecules to generate oxygen, but this process isn't perfectly efficient and requires ongoing maintenance and replacement parts. Over centuries or millennia, even small losses would become significant, while system degradation would be inevitable as components age and fail. Food production would require converting a spacecraft into a spacefaring farm. While hydroponic and aeroponic technologies show promise for growing crops in space, maintaining agricultural productivity for millennia without soil degradation, nutrient depletion, or crop disease would be extraordinarily difficult. The energy requirements for artificial lighting alone would place enormous demands on the spacecraft's power systems. Perhaps the most fundamental resource challenge involves the closed-loop ecosystem itself. Earth's biosphere has evolved over billions of years to achieve a delicate balance among countless species. Our attempts to create artificial closed ecosystems have consistently failed after relatively short periods. The most famous experiment, Biosphere 2, struggled with oxygen levels, crop yields, and ecosystem stability after just 2 years. Every resource aboard a generation ship would need to be endlessly recycled with near-perfect efficiency. Human waste would need to be completely processed back into usable nutrients for food production. Dead organic matter would need to be decomposed and its elements returned to the biological cycle. Any losses or inefficiencies in these systems would compound over time, eventually leading to critical resource shortages. Mechanical systems present their own sustainability challenges. Every pump, filter, dot, valve, fan, and electronic component has a finite operational lifespan, while redundancy and repair capabilities could extend system functionality. Eventually, every component would need replacement. This would require either carrying an impractical number of spare parts or having complete manufacturing capabilities aboard the spacecraft. Manufacturing capabilities create another layer of resource challenges. Producing new components requires raw materials, energy, and specialized equipment, mining, refining, and fabrication processes typically rely on extensive industrial infrastructures that would be impossible to fully replicate within the confines of even a very large spacecraft. Even 3D printing and other advanced manufacturing technologies require feedstock materials that would eventually be depleted. The energy required to power life support systems, agriculture, manufacturing, and other essential functions would be enormous and sustained. Solar power becomes increasingly impractical as a spacecraft moves away from stars, while nuclear power sources would require fuel supplies that would eventually be exhausted. Even theoretical fusion reactors would require deuterium or other fuel sources that would need to be stored or somehow harvested during the journey. The spacecraft's physical structure itself would face degradation over millennia. Materials fatigue, radiation damage, micrometeorite impacts, and general wear would accumulate over time. Critical structural components might need replacement, but replacing major structural elements of a spacecraft while in deep space exceeds our current engineering capabilities by orders of magnitude. Waste management represents another often overlooked challenge. Not all waste can be perfectly recycled, and toxic or hazardous byproducts would accumulate over time. Storage space for such materials would be finite, while improper handling could contaminate critical systems or living spaces. Medical resources would face similar sustainability issues. Pharmaceutical supplies have finite shelf lives, and maintaining production capabilities for all potentially needed medications would require extensive chemical synthesis facilities. Medical equipment would deteriorate and require replacement, while maintaining the knowledge and skills for all potential medical needs across generations would be extraordinarily difficult. Perhaps most challenging would be maintaining the technological infrastructure necessary for spacecraft operations over thousands of years. Computer systems, sensors, navigation equipment, and other electronic components have relatively short operational lifespans compared to the mission duration. Continuous replacement would be necessary, requiring not just manufacturing capabilities but the preservation of increasingly archaic knowledge as technologies evolved over generations. The compounding effect of even small inefficiencies in resource recycling, combined with the inevitable degradation of physical systems over time, creates a sustainability barrier that may be fundamentally insurmountable for missions measured in millennia rather than years or decades. These challenges aren't merely engineering problems awaiting clever solutions. They represent fundamental limits of closed-system thermodynamics and material science that may have no practical workarounds at the scales required for galactic center exploration. Beyond the physical and resource challenges of interstellar travel lies a dimension of difficulty that's often overlooked, but perhaps equally insurmountable: the psychological barriers of intergenerational space travel. The mental and social challenges of life aboard a generation ship would be unlike anything humans have ever experienced, creating obstacles that may be as limiting as the physical constraints we've discussed. Imagine being born on a spacecraft, living your entire life within its confines, and dying there without ever setting foot on a planet. This would be the reality for potentially hundreds of generations of travelers on a mission to the galactic center. The psychological impact of such an existence is difficult to predict, but evidence from isolated environments on Earth suggests it would be profound and potentially devastating. The most extreme isolation experiments conducted on Earth typically last only a few years at most. Projects like Mars mission simulations or Antarctic winter over cruise provide some insights into isolation psychology. But these participants always know their isolation has a defined endpoint. Generation ship inhabitants would have no such comfort. Their entire existence would be confined to the spacecraft, with no possibility of ever experiencing the natural world. Perhaps the most fundamental psychological challenge would be maintaining a sense of purpose across generations. The original crew might be highly motivated by the mission's scientific goals and the pioneering aspect of their journey. But what about their great-great-grandchildren? Would the 50th generation still feel connected to a mission conceived centuries before their birth? Historical evidence from Earth suggests that maintaining cultural continuity and shared purpose over even a few generations is extraordinarily difficult. The absence of natural environments would likely create profound psychological stress. Humans evolved in open spaces with natural light cycles, weather patterns, and diverse ecosystems. Our psychology is fundamentally shaped by these experiences. Studies of submariners, Antarctic researchers, and space station crews consistently show that prolonged existence in artificial environments leads to increased rates of depression, anxiety, sleep disorders, and interpersonal conflicts. The confined space of even a very large generation ship would inevitably create a sense of crowding and lack of privacy. Personal space is a fundamental human need, and its absence creates stress that compounds over time. The inability to ever truly get away from other crew members would likely lead to social tensions that could threaten mission cohesion across generations. Another psychological challenge would be the complete absence of novel experiences over time. Human brains are wired to seek novelty, new environments, new people, new challenges. On Earth, we can travel to new places, meet new people, or learn new skills when we feel stagnant. On a generation ship, the physical environment would remain unchanged throughout one's entire life. This lack of environmental variation would likely lead to chronic boredom, depression, and possibly even cognitive impacts as the brain responds to sensory monotony. The knowledge that one's entire existence is in service of a mission whose completion will only be witnessed by distant descendants could create existential distress. Human psychology is generally oriented toward goals that can be achieved within one's lifetime. The inability to ever see the mission's culmination could lead to a sense of purposelessness that might be psychologically devastating. Social organization over multiple generations presents another layer of challenge. How would leadership be structured? Would the original mission's organizational hierarchy be maintained, or would new social structures emerge over time? History shows that human societies rarely maintain stable governance systems over even a few centuries. Power struggles, ideological shifts, and social reorganization are the norm, not the exception. In human societies, the risk of cultural drift or even mission abandonment would increase with each passing generation. As the Earth receded into ancestral memory and the destination remained distant, intermediate generations might reasonably question why they should maintain the mission parameters established by long-dead ancestors for the benefit of unborn descendants. They might decide to alter course, slow down to conserve resources, or even abandon the original mission entirely in favour of more immediate concerns. Religious and ideological shifts would be almost inevitable over multi-generational timeframes. Earth's history demonstrates that religious beliefs and cultural values can transform dramatically even over relatively short periods. Such shifts could either reinforce the mission's importance, perhaps elevating it to a sacred duty, or undermine it by prioritizing different values or goals than those of the founders. The multi-generational spacecraft would also face unique challenges related to childhood development. Children born on the ship would never experience many fundamental aspects of normal human development. They would never feel natural gravity, see an open sky, experience weather, or encounter animals and plants outside of carefully maintained ship ecosystems. The psychological and developmental impacts of such an unusual childhood environment are unknown, but potentially significant. Information control would present another psychological challenge. Should later generations be taught about the full diversity of life and experience they're missing on Earth, potentially creating dissatisfaction with their limited existence? Or should education be narrowly focused on ship operations and mission parameters, effectively limiting their worldview to their immediate environment? Either approach carries significant ethical and psychological implications. Conflict resolution becomes critically important in an environment from which no one can leave. On Earth, individuals can physically separate from conflict situations by relocating. On a generation ship, Coexistence would be mandatory, potentially exacerbating tensions over time. Effective conflict management systems would be essential but extraordinarily difficult to maintain over centuries of social evolution. Perhaps most fundamentally, the psychological well-being of generation ship inhabitants would depend on maintaining a delicate balance between two opposing needs: the need for stability and continuity to ensure mission success, and the need for cultural adaptation and evolution to accommodate changing conditions and maintain psychological health. This balance has never been successfully maintained in any human society for the timescales required for interstellar travel. The combined weight of these psychological barriers suggests that maintaining a functioning human society aboard a generation ship for thousands of years may be not just challenging but fundamentally impossible given the constraints of human psychology. Our mental and social adaptations evolved for life on Earth in small, mobile groups with diverse environments and experiences, conditions diametrically opposed to those of intergenerational space travel. Even if we could somehow overcome all the previously discussed barriers, the vast distances, propulsion limitations, radiation hazards, resource sustainability challenges, and psychological obstacles, we would still face the enormously complex challenge of actually navigating a spacecraft across 26,000 light-years of largely uncharted space to precisely locate the galactic center. Navigation across interstellar distances represents a problem of such mind-boggling complexity that our current capabilities aren't just inadequate, they're almost comically insufficient. The first fundamental challenge is establishing and maintaining an accurate trajectory over thousands of years. Even the most minute error in initial course calculations would compound over time, potentially missing the target by trillions of miles. Consider that our most precise interplanetary navigation today, sending probes to Mars or other planets in our solar system, sometimes results in targeting errors of several kilometers, despite the relatively short distances involved. Scaling this precision up to interstellar distances reveals the magnitude of the challenge. A targeting error of just 1 part in a billion would result in missing the galactic center by 26,000 kilometers, a relatively small error by cosmic standards, but catastrophic for mission success. The problem becomes even more complex when we consider that space isn't static. The stars we use as navigational references are themselves moving. Our galaxy is in constant motion, with stars orbiting the galactic center at different speeds depending on their distance from it. The star patterns we see today will gradually shift over time, rendering traditional celestial navigation increasingly unreliable as the journey progresses. This stellar movement means that navigational charts would need to incorporate the predicted positions of reference stars thousands of years in the future, predictions that would inevitably contain errors that would accumulate over time. By the time a ship approached the galactic center after thousands of years of travel, the actual positions of stars could differ significantly from their predicted locations, complicating final approach navigation. Maintaining navigational accuracy would require constant measurement and course correction throughout the journey. However, determining a spacecraft's precise position in three-dimensional space becomes increasingly difficult as distance from Earth increases. Current methods rely heavily on communication with Earth-based systems, which would be impossible over interstellar distances due to the enormous communication delays. A generation ship would need to rely on autonomous navigation systems that could function reliably for thousands of years without external calibration or assistance. This would require not just extraordinary technological reliability, but also the ability to make complex navigational calculations based on stellar observations alone. Such systems would need to function flawlessly for a duration many thousands of times longer than any technology humans have ever created. The journey would also require navigating through largely unmapped regions of space. Our current maps of the galaxy are extremely coarse, showing only the largest and most luminous objects. Countless smaller objects, from rogue planets to asteroid fields to dense clouds of interstellar gas and dust, remain undetected and unmapped. Any of these could pose serious hazards to a spacecraft traveling at high velocity. Dense interstellar clouds present particular navigational challenges. These clouds can span light years and contain gas and dust that could damage a spacecraft traveling at high speed. Some regions of the galaxy contain ionized gas that could interfere with sensors and navigation systems. Without detailed maps of these hazards, plotting a safe course would be nearly impossible. The complex gravitational landscape of the galaxy creates additional navigational complications. Every mass in the galaxy, from stars to black holes to dark matter, exerts gravitational influence that affects the trajectory of passing objects. Calculating the combined gravitational effects of billions of objects on a spacecraft's path over thousands of years exceeds our current computational capabilities. As the ship approached the galactic center, these navigational challenges would intensify dramatically. The stellar density near the galactic center is thousands of times higher than in our solar neighborhood. Navigating through this stellar traffic jam would require extraordinarily precise calculations and maneuvers to avoid gravitational disruptions or actual collisions with stars or their surrounding planetary systems. The final approach to the galactic center would be further complicated by the extreme environment surrounding Sagittarius A star. The powerful gravitational field of the supermassive black hole distorts space-time itself, creating gravitational lensing effects that would distort observations and complicate navigational calculations. The intense radiation environment would likely interfere with sensors and computational systems, precisely when navigational precision would be most critical. Time dilation effects near the galactic center would create additional navigational complexities. As a spacecraft approached regions of stronger gravity, time would pass at different rates for different parts of the navigational system. Coordinating observations and calculations across these time differentials would require a level of relativistic navigation far beyond our current capabilities. Communication with Earth would be impossible due to the 26,000-year delay, meaning that any navigational assistance or course correction advice from mission control would be useless. The ship would need to be completely autonomous in its decision-making, responding to navigational challenges without any external guidance or support. Even determining when the ship had actually reached its destination would be challenging. The galactic center isn't a precise point, but rather a region spanning many light years containing numerous objects of interest. Without clear navigational markers, determining the completion of the mission would be surprisingly difficult, especially given that the appearance of the galactic center would differ significantly from observations made from Earth due to the different viewing angle. The combination of these navigational challenges, precise trajectory calculation, compensation for stellar movement, autonomous operation over millennia, hazard avoidance, gravitational complexity, and the extreme environment of the galactic center creates a navigational problem that may be fundamentally unsolvable with any technology we can realistically envision. Even with substantial advances in computing, sensing, and autonomous systems, the sheer complexity and duration of the navigational task likely places it beyond practical human capability. The navigational challenges of interstellar travel reveal another critical barrier to galactic center exploration: the fundamental limitations of communication across such vast distances. Even if we could somehow overcome all the previously discussed obstacles and successfully navigate to the heart of our galaxy, we would be doing so in almost complete isolation, cut off from Earth by communication delays that render any meaningful exchange of information impossible. Radio waves and other electromagnetic signals, the foundation of all our current communication technologies, travel at the speed of light. This creates an unavoidable physical constraint. Any transmission from a spacecraft near the galactic center would take 26,000 years to reach Earth, and any response would take another 26,000 years to return to the spacecraft. This isn't simply an inconvenience. It fundamentally transforms the nature of the mission from an interactive exploration to what would essentially be a one-way journey into isolation. The practical implications of this communication delay are profound. Consider that mission control on Earth would have no way of knowing if the spacecraft encountered a critical problem just 1 year into its journey until 26,000 years later. Any advice or assistance would arrive 26,000 years after that, far too late to be of any use. The spacecraft and its crew would be entirely on their own from the moment they departed our solar system. This isolation means that any technical problems, medical emergencies, or critical decisions would need to be handled autonomously by the ship's crew without any external guidance or support. No matter how well trained the original crew might be, they could not possibly be prepared for every contingency that might arise over thousands of years of travel. And as knowledge passed to subsequent generations, critical expertise might be lost or diluted, further compromising the crew's ability to respond to challenges. The communication delay would also have significant scientific implications. One of the primary purposes of such a mission would presumably be to gather data about the galactic center and transmit it back to Earth. Yet the first data would not begin arriving until at least 26,000 years after launch, long after the original mission planners, their civilization, and possibly even their species had passed from existence. The scientists who eventually received this data would have no way to request clarification or additional observations. Even if we could somehow develop a perfect transmission system that could send signals across 26,000 light-years without degradation, itself an enormous technical challenge, the delay would still render traditional communication impossible. The mission would need to be entirely autonomous, carrying with it all the knowledge and decision-making capability it would need for the entire journey. There could be no consultation, no course corrections based on new information from Earth, and no updated mission parameters. Beyond the delay issue, the technical challenges of transmitting any signal across 26,000 light-years are staggering. Radio signals weaken with the square of distance, meaning that a signal travelling from the galactic centre to Earth would be billions of times weaker than signals sent from Mars or even the outer planets of our solar system. The power required to transmit a detectable signal across such distances would be enormous, far exceeding the energy generation capabilities of any spacecraft we could realistically build. Natural sources of radio emission throughout the galaxy would create significant interference, potentially drowning out any transmitted signal. The galactic centre itself is a particularly noisy radio environment, with numerous strong sources that would compete with any spacecraft transmission. Distinguishing an artificial signal from this natural background noise would be extraordinarily difficult, even with the most sensitive receivers. The technical requirements for a communications system that could function reliably for thousands of years present another layer of challenge. Electronic components degrade over time due to radiation exposure, thermal cycling, and simple wear. No communication system in human history has operated continuously for even 100 years, let alone the thousands required for a galactic center mission. The reliability engineering required for such longevity exceeds our current capabilities by orders of magnitude. Data storage presents similar durability challenges. Any information gathered during the journey would need to be stored for thousands of years before it could be transmitted back to Earth once the ship reached a position where such transmission became feasible. No current data storage technology has demonstrated reliability over such timeframes. The risk of data corruption or loss over millennia of storage would be substantial. The communication system would also need to account for changes in technology over the mission duration. What if, during the thousands of years of travel, Earth developed completely new communication technologies incompatible with the spacecraft's equipment? The ship might arrive at the galactic center ready to transmit valuable data, only to find that no one was listening on the frequencies it was using. Planning for technological evolution over such timeframes is practically impossible. Language and data format evolution present similar concerns. Human languages change significantly over centuries, sometimes becoming completely unintelligible to later generations. Computer languages and data formats become obsolete even faster. A message transmitted after thousands of years of travel might be received by people who could no longer understand it without extensive translation efforts. The isolation imposed by these communication limitations would likely have profound psychological impacts on the crew. Humans are fundamentally social beings who evolved in connected communities. The knowledge that one is completely cut off from the rest of humanity, that no call for help will ever be answered, that no news will ever arrive from home, that one's discoveries will not be shared for millennia, would create a psychological burden unlike anything humans have experienced before. Perhaps most fundamentally, the communication barrier transforms the nature of exploration itself. Throughout human history, exploration has been a dialogue between those who venture forth and those who remain behind. Explorers return with knowledge that shapes future expeditions. This iterative process has been central to human discovery. A mission to the galactic center would break this pattern completely, representing a profound departure from all previous models of human exploration. While communication across interstellar distances presents a fundamental barrier, the physical dangers of the interstellar medium itself pose an equally serious threat to any spacecraft attempting to reach the galactic center. Space is not empty. It's filled with matter that, while incredibly diffuse by Earth standards, becomes a serious hazard at the high velocities required for interstellar travel. The interstellar medium consists primarily of hydrogen gas, along with helium and traces of heavier elements, plus dust particles of various sizes. While this material is extremely tenuous, typically just a few atoms per cubic centimetre in our galactic neighbourhood, it becomes increasingly dense as one approaches the galactic centre, where concentrations can be thousands of times higher. For a spacecraft travelling at even a small fraction of the speed of light, these particles become dangerous projectiles. A single dust grain, 1/1000th of a millimetre in diameter, invisible to the naked eye, would impact with kinetic energy equivalent to a hand grenade if the spacecraft were travelling at just 10% of light speed. At higher velocities, the energy increases dramatically, potentially causing catastrophic damage to the spacecraft's hull or systems. The threat isn't limited to larger dust particles. Even individual atoms of hydrogen gas become significant hazards at relativistic speeds. When a spacecraft travelling at a substantial fraction of light speed collides with hydrogen atoms, the impacts cause atomic and subatomic reactions that generate secondary radiation, gradually degrading the ship's hull and potentially creating radiation hazards for the crew over the course of a journey spanning 26,000 light-years. The cumulative effect of these impacts would be substantial. A spacecraft travelling to the galactic centre would collide with a total mass of interstellar material that, while small compared to the ship itself, would deliver its energy in a highly focused manner at specific impact points. Over time, these impacts would erode the spacecraft's external surfaces, potentially compromising structural integrity or critical systems. Protecting against these impacts presents enormous engineering challenges. Traditional physical shields would themselves be gradually eroded by the constant bombardment. Any shield massive enough to provide adequate protection throughout the entire journey would add substantially to the spacecraft's mass, exacerbating the already formidable propulsion challenges we've discussed. Some theoretical protection systems involve electromagnetic fields that could deflect charged particles, but these would be ineffective against neutral dust grains and would require enormous power supplies to maintain continuously for thousands of years. Other concepts involve sacrificial outer hulls designed to be gradually eroded, but the total mass required for adequate protection over such distances would likely be prohibitive. The problem becomes even more acute if the spacecraft must travel at higher velocities to make the journey in a somewhat reasonable time frame. The kinetic energy of impacts increases with the square of velocity, meaning that doubling the spacecraft's speed quadruples the energy of each collision. This creates a cruel paradox. Faster travel reduces journey time but exponentially increases collision hazards. The distribution of matter in the interstellar medium isn't uniform, further complicating navigation and protection strategies. Dense molecular clouds, common throughout the galaxy and particularly near the galactic center, contain significantly higher concentrations of gas and dust. Passing through such a cloud at high velocity could subject the spacecraft to damage equivalent to flying through a sandstorm at hypersonic speeds. Our current maps of the interstellar medium are extremely coarse, showing only the largest and densest clouds. Countless smaller concentrations remain undetected and unmapped. Planning a safe trajectory through 26,000 light-years of partially mapped space would be nearly impossible, particularly given that the environment would change significantly during the thousands of years of travel time. The region surrounding the galactic center presents particularly hazardous conditions. The intense radiation and stellar winds from the concentrated population of stars near the core create complex interactions with the interstellar medium. Shock fronts, ionized regions, and turbulent gas flows would all present unique hazards to a spacecraft passing through the region. Detecting hazards in advance becomes increasingly difficult at higher velocities, at a significant fraction of light speed. The time between detecting a dangerous concentration of matter and impacting it could be seconds or less, insufficient for course corrections or shield reinforcement. This creates another paradox. The faster the spacecraft travels, the less time it has to detect and respond to hazards. Even if a perfect detection system could be developed, the ability to perform course corrections would be limited by the spacecraft's maneuverability. Changing the trajectory of an enormous generation ship would require tremendous energy and could only be accomplished gradually. Sudden, evasive maneuvers to avoid detected hazards would likely be impossible given the inertia of such a massive vessel. The continuous bombardment by interstellar particles would also affect sensors and external scientific instruments. Optical surfaces would be gradually pitted and degraded, potentially blinding the spacecraft to its surroundings. Sensor degradation would be particularly problematic during the final approach to the galactic center, precisely when accurate environmental assessment would be most critical. For a generation ship carrying a human population, the risks of catastrophic hull breach due to particle impacts cannot be overstated. Even a small breach could lead to rapid decompression of habitat areas, potentially resulting in mass casualties. The psychological burden of living under constant threat of such catastrophic failure would add to the already substantial mental health challenges of interstellar travel. The combination of these collision hazards, from atomic hydrogen to microscopic dust to larger particles, increasing density near the galactic center, detection limitations, and the cruel mathematics of kinetic energy at high velocities, creates yet another layer of challenge that may be fundamentally insurmountable for human exploration of the galactic center. The interstellar medium's dangers highlight another fundamental obstacle to galactic center exploration: the biological limitations of the human body itself. Our physical form evolved specifically for life on Earth under very particular conditions that cannot be replicated during interstellar travel without extraordinary measures. The human body simply isn't designed for long-duration spaceflight, and these biological constraints may ultimately prove as limiting as any technological challenge. The most immediate biological concern is the effect of microgravity or zero gravity on human physiology. Studies of astronauts who have spent extended periods on the International Space Station have documented a range of significant health impacts, including bone density loss at a rate of approximately 1 to 2% per month, muscle atrophy, cardiovascular changes, immune system suppression, and vision problems caused by fluid shifts within the body. These effects occur after just months in space. Now imagine the compounding effects over years, decades, or generations. While exercise and certain medications can mitigate some of these effects, they cannot eliminate them entirely. Long-term exposure to microgravity leads to changes that may be irreversible, particularly in skeletal structure. After just 1 year in space, some astronauts struggle to walk normally upon returning to Earth's gravity. The implications for humans born and raised in low or zero gravity are even more severe. Their bodies would develop without the stress of gravity that shapes proper bone and muscle formation, potentially making them unable to ever function in Earth-like gravity. One potential solution often proposed is artificial gravity generated through rotation of the spacecraft. However, the engineering challenges of creating rotating habitats large enough to avoid motion sickness caused by the Coriolis effect in small radius rotating systems would require enormous structures far larger than anything humans have ever built in space. Maintaining such systems over thousands of years presents additional engineering and resource challenges we've already discussed. The radiation environment of deep space presents perhaps an even more serious biological barrier. The human body can only tolerate certain levels of radiation exposure before suffering acute radiation sickness, increased cancer risk, and genetic damage. Earth's magnetic field and atmosphere shield us from the majority of cosmic radiation, but in deep space, no such natural protection exists. Even with the best radiation shielding we could practically build into a spacecraft, humans would be exposed to radiation levels far exceeding what is considered safe for lifetime exposure on Earth. The biological impact of this radiation would be cumulative and multi-generational. Each successive generation would inherit the genetic damage from their parents, while accumulating additional damage of their own, over dozens or hundreds of generations. This would likely lead to increasing rates of cancer, birth defects, and other health problems that would threaten the viability of the crew population. The human genome has not evolved to withstand such continuous radiation exposure, and there may be no technological solution that can adequately address this fundamental biological incompatibility. Reproduction and child development in space present additional biological challenges that remain largely unexplored. No human has ever been conceived or born in space, and studies on mammalian reproduction in microgravity raise significant concerns. Experiments with rats and mice have shown disruptions to hormone systems, fetal development issues, and increased rates of failed pregnancies in space-like conditions. The proper development of human embryos requires specific gravitational cues that guide cell differentiation and organ formation, processes that might be seriously compromised in microgravity. The immune system presents another biological limitation. Studies of astronauts show that extended time in space leads to altered immune function, with some aspects becoming suppressed while others shift into overactive inflammatory responses. At the same time, bacteria and viruses have been shown to become more virulent in microgravity environments. This combination, weakened human immunity and strengthened pathogens, creates a dangerous situation for long-term space habitation. The closed environment of a generation ship would also create unique challenges for the human microbiome, the collection of beneficial bacteria that live in and on our bodies. On Earth, we constantly exchange microbes with our environment and other humans, maintaining a healthy diversity. In the isolated environment of a spacecraft, microbial diversity would likely decrease over generations, potentially leading to dysbiosis and related health problems affecting digestion, immunity, and even mental health, as the gut-brain connection becomes increasingly understood in medical science. The sensory environment of a spacecraft would also be fundamentally different from what human biology evolved to expect. Our nervous systems developed to process natural variations in light, sound, temperature, and other sensory inputs. The artificial environment of a spacecraft, with its constant mechanical sounds, artificial lighting, and limited sensory variation, would likely have subtle but significant effects on neurological development and function over time. The psychological impacts of such an environment, which we discussed earlier, have direct biological correlates. Chronic stress, isolation, and confinement lead to measurable changes in hormone levels, brain function, and even gene expression. These biological changes can manifest as sleep disorders, cardiovascular problems, and compromised immune function, creating a feedback loop of psychological and physical health challenges. Aging itself may present unique challenges in the space environment. The processes of cellular aging appear to accelerate in microgravity and high radiation environments. Telomere dynamics, oxidative stress, and DNA repair mechanisms, all critical aspects of the aging process, function differently in space than on Earth. This could potentially shorten lifespans or increase the burden of age-related diseases among the ship's population over time. Perhaps most fundamentally, human biology is the product of evolution in Earth's specific environment, its gravity, atmosphere, microbiome, seasonal changes, day-night cycles, and countless other factors that have shaped our development over millions of years. Removing humans from this environment for generations means placing our biology in conditions for which it was never adapted. The compounding effects of this biological mismatch over multiple generations might produce changes we cannot fully predict or mitigate. The limitations of human biology for long-duration spaceflight aren't merely technical problems awaiting clever engineering solutions. They represent fundamental mismatches between the conditions our bodies evolved to thrive in and the realities of the space environment. Even with significant biomedical advances or potential genetic modifications, the gap between what our biology requires and what the space environment provides may prove too wide to bridge for missions measured in millennia. While biological limitations represent one set of insurmountable challenges for galactic center exploration, the energy requirements for such a journey present an equally fundamental barrier. The sheer magnitude of energy needed to accelerate a human-carrying spacecraft to a significant fraction of light speed and later decelerate it exceeds our current and projected future capabilities by many orders of magnitude, creating what may be the most fundamentally limiting factor of all. To understand the scale of this energy challenge, we need to consider basic physics. The kinetic energy of a moving object increases with the square of its velocity. This means that doubling a spacecraft's speed requires 4 times the energy. To reach even 10% of light speed, still requiring centuries for a journey to the galactic center, the energy requirements are staggering. Let's consider some numbers to illustrate this point. A modestly sized generation ship capable of supporting a small human population might have a mass of around 10,000 tons, roughly comparable to a small naval vessel. Accelerating this mass to 10% of light speed would require approximately 4.5 times 10 to the 19th joules of energy. For comparison, this is roughly equivalent to the total energy consumption of human civilization for an entire year. And this calculation assumes perfect efficiency in converting energy to motion, something no propulsion system can achieve. The energy problem becomes even more daunting when we consider that the spacecraft would need to carry fuel not just for initial acceleration, but also for deceleration upon reaching the target, plus maneuvering, and powering life support systems throughout the journey. So, the rocket equation, which governs the relationship between a vehicle's mass, velocity change, and propellant requirements, creates a vicious exponential relationship. The more fuel you need, the more fuel you need to carry to accelerate that fuel, and so on. Nuclear fusion, often proposed as a solution to interstellar travel's energy needs, still falls far short of the requirements. Even if we developed perfectly efficient fusion reactors using deuterium-tritium or more advanced fusion fuels, the mass of fuel required would still far exceed what could reasonably be carried by the spacecraft. A fusion-powered ship attempting to reach 10% of light speed would need to carry many times its own mass in fuel, a practical impossibility. Antimatter, the most energy-dense fuel theoretically possible under known physics, releases energy equivalent to the complete conversion of mass to energy as described by Einstein's famous equation E equals mc squared. Even with antimatter, however, the fuel mass requirements remain prohibitive. To accelerate our hypothetical 10,000-ton ship to 10% of light speed would require approximately 100 tons of antimatter, an amount we could not produce in millions of years at our current or near-future production capabilities, which measure annual antimatter production in nanograms. The storage of such energy presents its own insurmountable challenges. Antimatter must be contained in magnetic fields since it annihilates upon contact with regular matter. The energy density would be so high that containment failure would result in an explosion dwarfing the most powerful nuclear weapons ever created. No known or theoretical containment system could safely store the quantities of antimatter required for interstellar travel. External energy sources, such as massive laser arrays powering light sails, have been proposed to avoid carrying fuel on board. However, such systems would require construction of infrastructure dwarfing anything humanity has ever built. A laser powerful enough to accelerate a generation ship to interstellar velocities would consume more power than our entire civilization currently generates, and would need to maintain its beam on the target with perfect precision over interstellar distances for years or decades. The energy requirements don't end with propulsion. A generation ship would need to generate power for life support, agriculture, manufacturing, computing, and countless other systems throughout a journey lasting millennia. This continuous energy demand would require power generation systems of unprecedented reliability and longevity. Solar power becomes increasingly impractical as the spacecraft moves away from stars, while nuclear power sources would require fuel supplies that would eventually be exhausted. The energy systems themselves face fundamental engineering challenges related to waste heat. Any energy used aboard the spacecraft eventually becomes heat that must be radiated away to avoid cooking the inhabitants. In the vacuum of space, getting rid of waste heat is surprisingly difficult. It can only be done through thermal radiation, which requires large radiator surfaces that add mass and complexity to the spacecraft, while creating additional points of potential failure. Even if we could somehow solve the initial acceleration energy requirements, the spacecraft would face the challenge of deceleration upon reaching the galactic center. Without some method of using the interstellar medium or destination star system for braking, the spacecraft would need to carry additional fuel specifically for deceleration, effectively doubling the already insurmountable energy requirements of the mission. The combination of these energy factors, the enormous initial acceleration requirements, the tyranny of the rocket equation, the limitations of even theoretical fuels like antimatter, the continuous power needs throughout the journey, waste heat management, and deceleration requirements creates an energy barrier that may be truly insurmountable under the laws of physics as we understand them. This energy barrier isn't merely a matter of developing more advanced technology or more efficient engines. It represents a fundamental limit imposed by the relationship between mass, energy, and velocity in our universe. While science fiction often invokes warp drives, hyperspace, dot, or other speculative technologies to circumvent these limitations, such concepts remain firmly in the realm of fiction, with no clear path toward practical realization under known physical laws. The fundamental energy limitations of interstellar travel become even more problematic when we consider another significant hazard awaiting any spacecraft attempting to reach the galactic center: the dramatically increasing stellar density as one approaches the core of our galaxy. Unlike our relatively spacious cosmic neighborhood, the galactic center presents an environment where stars are packed together with frightening proximity, creating navigational and safety challenges that may be impossible to overcome. In our solar neighborhood, stars typically sit at comfortable distances of several light years apart. Our nearest stellar neighbor, Proxima Centauri, is about 4 light years away, a vast distance by human standards, but relatively sparse in cosmic terms. This spacing gives planets and spacecraft plenty of room to maneuver without worrying about close stellar encounters. As one travels toward the galactic center, however, this comfortable spacing gradually disappears. At roughly 1,000 light-years from the center, stellar density increases to the point where stars are typically only around 1/10 of a light-year apart. By the time you reach the innermost 100 light-years, this distance shrinks dramatically, with some stars separated by as little as a few light days or even light hours. The central parsec, roughly 3 light-years, around Sagittarius A star, contains an estimated 10 million stars packed into a volume that would contain just a handful of stars in our neighborhood. This extreme density creates what astronomers call the nuclear star cluster, the densest collection of stars in our entire galaxy. This stellar crowding creates several severe problems for any spacecraft attempting to navigate through the region. First, and most obviously, the risk of an actual physical collision with a star increases dramatically. While space remains mostly empty even in these dense regions, the sheer number of stars means that plotting a safe trajectory becomes exponentially more complex. A navigation error that might be inconsequential in our stellar neighbourhood could be catastrophic near the galactic centre. Even if a spacecraft managed to avoid direct collisions with stars, it would face the equally dangerous prospect of passing through planetary systems. Each star potentially hosts planets, asteroid belts, and comets, all presenting collision hazards. The dense packing of stars means that these systems overlap significantly, creating vast regions where space debris from multiple star systems creates an obstacle course of potentially deadly objects. Perhaps even more dangerous than physical collisions is the gravitational complexity of the galactic center region. Each star exerts gravitational pull that affects the trajectory of passing objects. In regions where stars are densely packed, these overlapping gravitational fields create an extraordinarily complex gravitational landscape that changes constantly as stars move in their orbits. A spacecraft attempting to navigate through this region would need to continuously calculate and adjust for the gravitational influence of thousands of nearby stars, a computational task of staggering complexity. Even small miscalculations could send the craft veering off course, potentially into the path of a star or into a region of even greater hazard. The types of stars found near the galactic center present additional hazards. The region contains a high concentration of massive, hot stars that emit intense radiation and powerful stellar winds. These stars have much larger danger zones around them where radiation levels would damage or destroy a spacecraft. Some also undergo frequent flaring events that can temporarily increase their dangerous emissions by orders of magnitude with little warning. The galactic center also hosts an unusually high concentration of stellar remnants, neutron stars and stellar mass black holes left behind after massive stars end their lives in supernova explosions. These extremely dense objects are particularly dangerous because they're difficult to detect directly but exert powerful gravitational effects that could capture or destroy a passing spacecraft. The dynamic nature of the galactic center compounds these navigational challenges. Stars in this region move at much higher velocities relative to each other than they do in the galaxy's outer regions. Some stars in the central parsec orbit the supermassive black hole at speeds exceeding 1,000 kilometers per second. This means that the navigational environment isn't just complex, it's rapidly changing, requiring constant updates to any planned trajectory. Another significant hazard is the presence of dense gas and dust clouds throughout the galactic center region. These clouds can span light years and contain material that would damage a spacecraft traveling at high velocity. Some regions contain molecular clouds dense enough to cause significant drag on a passing spacecraft, potentially altering its trajectory or causing structural damage through uneven deceleration forces. The presence of Sagittarius. A star itself creates additional hazards through its influence on the surrounding space. The supermassive black hole occasionally captures and consumes gas, dust, or even whole stars, creating accretion events that can dramatically increase radiation levels throughout the surrounding region. These events are unpredictable and could create suddenly lethal conditions for any spacecraft in the vicinity. Navigating safely through this stellar obstacle course would require detection systems far more advanced than anything we currently possess. A spacecraft would need to simultaneously track thousands of objects, predict their movements, calculate their gravitational influences, monitor radiation levels, and continuously update its trajectory to avoid hazards, all while traveling at velocities that would give it minimal response time to newly detected threats. The combined effect of these hazards, the extreme stellar density, complex gravitational interactions, high-energy star types, stellar remnants, rapidly changing conditions, gas and dust clouds, and the unpredictable influence of Sagittarius A star creates an environment fundamentally hostile to safe navigation by any spacecraft we could realistically design. Unlike many other challenges of interstellar travel that might be overcome with sufficient technological advancement, the crowded, chaotic nature of the galactic center may represent a hazard that simply cannot be safely navigated by physical spacecraft carrying fragile human cargo. The stellar density challenges of the galactic center are further complicated by the fundamental physics described in Einstein's special theory of relativity, which imposes absolute limits on space travel that no amount of technological advancement can overcome. These relativistic effects become increasingly significant as a spacecraft approaches the speeds necessary to make interstellar journeys practical, creating obstacles that may ultimately prove more limiting than any engineering challenge. The most fundamental relativistic barrier is the absolute speed limit imposed by the speed of light in vacuum, approximately 300,000 kilometers per second. This isn't merely a current technological limitation but a fundamental law of physics. No object with rest mass can reach or exceed this speed. This creates an absolute ceiling on how fast a spacecraft could potentially travel, no matter how advanced our technology becomes. This speed limit means that even in the most optimistic scenario, a spacecraft somehow accelerated to just below the speed of light, the journey to the galactic center would still take more than 26,000 years from the perspective of observers on Earth. While time dilation effects would make the journey seem shorter to the crew aboard the spacecraft, they would still experience thousands of years of subjective time during the journey. The relationship between energy and velocity becomes increasingly problematic as a spacecraft approaches significant fractions of light speed. According to relativistic mechanics, the energy required to accelerate an object grows asymptotically as its velocity approaches the speed of light. In practical terms, accelerating from 90% to 95% of light speed requires more energy than accelerating from 0 to 90%. This creates an inescapable energy barrier that becomes exponentially worse as a spacecraft approaches speeds that would make interstellar journeys feasible within human lifespans. The energy requirements become not just impractically large, but physically impossible to accommodate within any spacecraft design as velocities approach the speed of light. Mass increase is another relativistic effect that creates fundamental problems for high-speed travel. As an object's velocity increases, its relativistic mass also increases. At 90% of light speed, an object's mass is more than twice its rest mass. At 99%, it's more than 7 times its rest mass. This mass increase affects not just the energy requirements for further acceleration, but also makes the spacecraft more difficult to maneuver or decelerate. The increased relativistic mass also affects how the spacecraft interacts with the interstellar medium. As mass increases, so does the effective impact energy of collisions with gas and dust particles. A spacecraft traveling at 99% of light speed would experience collision energies with interstellar hydrogen atoms sufficient to trigger nuclear reactions, potentially creating radiation hazards for the crew and degrading the spacecraft structure through nuclear spallation. Time dilation, while often suggested as a benefit that could make the journey seem shorter for the crew, creates its own set of challenges. At high relativistic speeds, time passes significantly more slowly on the spacecraft than it does on Earth. While this means the crew might experience only a few decades of travel time, it also means they would become completely temporally disconnected from the civilization they left behind. A spacecraft returning from a round trip to the galactic center at high relativistic speeds might find that tens of thousands of years had passed on Earth, rendering their mission, its purpose, and their connection to human civilization potentially meaningless. The crew would effectively be time travelers launched into Earth's distant future, not explorers who could share their discoveries with the civilization that sent them. The relativistic effects on perception and navigation create additional challenges. At speeds approaching the speed of light, the apparent positions of stars and other objects become significantly distorted due to the relativistic aberration of light. Light from objects directly ahead appears blue-shifted, while light from objects behind appears red-shifted. The night sky would appear dramatically distorted, with stars seemingly concentrated in the direction of travel. This relativistic aberration would make traditional stellar navigation extremely difficult, requiring complex calculations to determine the true positions of reference stars. Combined with Doppler shifting of light from reference objects, these effects would require navigation systems of extraordinary sophistication to function at relativistic velocities. Another rarely discussed relativistic effect involves the apparent compression of space in the direction of travel. At high relativistic speeds, distances in the direction of motion appear contracted from the perspective of the spacecraft. While this might seem advantageous, it actually creates severe problems for collision avoidance. Objects that are physically distant from each other would appear to be much closer together from the perspective of the rapidly moving spacecraft, making navigation through fields of objects, like the crowded galactic center, extraordinarily difficult. The extreme blue shifting of radiation encountered during high-speed travel presents another serious hazard. Even the low-energy photons of the cosmic microwave background would be blue-shifted to potentially harmful energy levels for a spacecraft traveling at very high fractions of light speed. Radiation that would be harmless to a stationary object becomes increasingly energetic and dangerous as relative velocity increases. Perhaps most fundamentally, the relativistic barrier means that there can never be real-time control or communication with an interstellar spacecraft. The combination of distance and relativistic effects ensures that any mission must be completely autonomous, with no possibility of guidance or assistance from Earth once the journey begins. The combination of these relativistic effects, the light speed limit, energy-velocity relationship, mass increase, time dilation, perceptual distortions, space contraction, radiation blue shifting, and communication impossibilities creates a barrier to galactic center exploration that is not merely technological but fundamental to the physics of our universe. No foreseeable advancement in propulsion technology, materials science, or spacecraft design can overcome these basic physical limitations, which may ultimately confine human exploration to a relatively small region of our vast galaxy. Beyond the fundamental physics barriers imposed by relativity, any spacecraft attempting to reach the galactic center would face a more mundane but equally devastating challenge: the gradual degradation of its physical materials in the harsh environment of deep space. This material breakdown operates on timescales far shorter than the journey itself, creating an engineering paradox that may be impossible to resolve regardless of technological advancement. All materials, no matter how advanced, undergo degradation processes when exposed to the space environment. These processes occur slowly by human standards, but over the millennia required for a journey to the galactic center, they would compromise virtually every component of a spacecraft. The most obvious degradation comes from radiation exposure. High-energy particles from cosmic rays, solar wind, and other sources gradually damage materials at the atomic and molecular levels, breaking chemical bonds and displacing atoms from their normal positions in material structures. For metals, this radiation damage leads to embrittlement and increased susceptibility to stress fractures. Aluminum, commonly used in spacecraft construction, becomes increasingly brittle as radiation breaks down its crystalline structure. Even small amounts of embrittlement can have catastrophic consequences when materials are under the constant mechanical stress of a working spacecraft. Over thousands of years, radiation would transform once flexible and resilient materials into fragile shadows of their former selves. Polymers and composite materials fare even worse under radiation exposure. The long molecular chains that give these materials their useful properties gradually break down under radiation bombardment. Materials like Kevlar, carbon fiber composites, and various plastics that might be used for habitat structures, wiring insulation, or seals would degrade significantly in just decades, let alone the millennia required for galactic center travel. This degradation typically manifests as increased brittleness, reduced tensile strength, and changes in crucial properties like electrical resistance or thermal conductivity. Semiconductor materials used in electronics and solar cells are particularly vulnerable to radiation damage. A single high-energy particle can displace thousands of atoms in a semiconductor crystal, creating defects that compromise electrical performance. Over time, these defects accumulate, causing electronic components to fail. While modern spacecraft use radiation-hardened electronics, even these specialized components are designed for missions lasting years or decades, not millennia. Beyond radiation, spacecraft materials face degradation from thermal cycling, the repeated heating and cooling that occurs as the spacecraft moves through varying radiation environments. As materials heat and cool, they expand and contract slightly. Over thousands of cycles, this leads to fatigue and eventual failure, particularly at joining points between different materials with different thermal expansion rates. Vacuum exposure creates its own degradation mechanisms. Many materials slowly outgas in vacuum, releasing trapped gases and volatile components. This outgassing can lead to material shrinkage, increased brittleness, and changes in mechanical properties. Some materials, particularly certain polymers, can lose significant mass through outgassing over extended periods, compromising their structural integrity and functional properties. Atomic oxygen, present in the sparse atmosphere of low Earth orbit and in trace amounts throughout interstellar space, presents another degradation mechanism. This highly reactive form of oxygen attacks carbon-based materials, gradually eroding their surfaces. While the concentration in interstellar space is extremely low, the accumulated exposure over thousands of years would still contribute to material degradation, particularly for exposed carbon-based components or coatings. Micrometeoroid impacts, while individually small, would accumulate over millennia to cause significant erosion of external surfaces. The spacecraft's hull would essentially undergo continuous sandblasting throughout its journey. Over time, this erosion would thin protective coatings, compromise thermal control systems, and potentially create weak points that could lead to more serious structural failures. Even in the absence of external factors, many materials undergo spontaneous degradation processes simply due to atomic and molecular movement over time. Metals can experience diffusion of atoms at interfaces, leading to weakened joints. Some alloys undergo phase separation over extended periods, changing their mechanical properties. Amorphous materials like glasses can slowly crystallize, becoming more brittle and less transparent. These time-dependent processes occur even under ideal conditions and cannot be completely eliminated. The most insidious aspect of material degradation is its unpredictability. While engineers can estimate general degradation rates based on laboratory tests and space exposure experiments, these typically involve accelerated aging techniques that may not perfectly replicate the effects of true long-term exposure. The combined effects of multiple degradation mechanisms operating simultaneously over thousands of years create outcomes that cannot be reliably predicted or tested in advance. For a generation ship to the galactic center, the material degradation problem creates a fundamental paradox. The ship would need to remain structurally and functionally intact for a period far longer than the service life of any material we can currently produce or reasonably envision. Even materials with the longest known service lives, certain ceramics or specialized metal alloys, have not demonstrated durability on timescales approaching what would be required. Maintenance and replacement strategies face equally daunting challenges. The ship would need to carry spare parts for every critical component, or more realistically, period, the means to manufacture replacements as needed. This would require not just the raw materials for manufacturing, but also production facilities that themselves would be subject to the same degradation processes. The ability to produce specialized components like computer chips or precision mechanical parts would require industrial capabilities difficult to maintain in a closed system. Some proposed solutions involve biological approaches, using living materials that can self-repair through growth and regeneration. However, biological materials have their own vulnerabilities to radiation and other space environment factors, and engineering biological systems that could maintain structural components for millennia exceeds our current capabilities by orders of magnitude. The reality is that material degradation doesn't just present a difficult engineering challenge, it imposes a fundamental temporal limit on how long any physical structure created by humans can be expected to function in space. This limit appears to fall well short of the time required for a journey to the galactic centre, creating yet another barrier that may be truly insurmountable regardless of technological advancement. The problem of material degradation connects directly to another fundamental challenge for galactic centre exploration: the inevitable obsolescence of the information used to plan and execute such a mission. Any spacecraft embarking on a journey to the galactic centre would be operating with information that becomes increasingly outdated as the mission progresses, creating dangers and inefficiencies that compound over time. The most basic form of this information problem concerns our knowledge of what actually exists at the galactic centre right now. Light from the galactic centre takes approximately 26,000 years to reach Earth, meaning that our current observations show the centre as it was 26,000 years ago, during the Upper Paleolithic period on Earth, when humans were painting cave walls and hunting mammoths. This means that any mission plan would be based on grossly outdated information. Stars observed in our current surveys might have gone supernova thousands of years ago, dramatically changing the radiation and gravitational environment. New stars might have formed, black holes might have merged, and the entire region could have undergone significant changes that would be completely unknown to mission planners. The problem becomes even more acute when considering the path between Earth and the galactic centre. The interstellar medium is not static. Gas clouds move and evolve. Stars migrate through space, and the entire galaxy rotates. A pathway that appears clear in our current observations might contain hazards that developed during the thousands of years since the light from those regions began its journey to our telescopes. Navigation planning becomes nearly impossible under these circumstances. Imagine planning a cross-country road trip using a map that shows the landscape as it existed 26,000 years ago, before modern cities, highways, or even the current courses of rivers existed. The actual landscape encountered would bear little resemblance to what was expected, rendering the original route planning largely useless. This information lag affects not just large-scale features, but also the detailed characteristics of specific targets. If the mission's goal included studying particular stars or phenomena near the galactic centre, those targets might no longer exist or might have transformed into entirely different objects by the time the spacecraft arrived. The scientific objectives of the mission would be based on questions relevant to our current understanding, which would likely be completely outdated by the time any observations could be made. The spacecraft itself would suffer from a different type of information obsolescence. The technology, scientific instruments, and research priorities incorporated into its design would reflect the state of knowledge at the time of its launch. Over the thousands of years of travel time, scientific understanding and technological capabilities on Earth would advance dramatically, potentially rendering the spacecraft's original mission parameters and equipment hopelessly primitive by the standards of the era when it actually reached its destination. This creates a cruel paradox. By the time a spacecraft could reach the galactic centre, the civilization that sent it would likely have developed much faster propulsion technology that could make the same journey in a fraction of the time. A spacecraft launched today might be passed en route by more advanced vehicles launched centuries or millennia later, making the original mission effectively pointless. Communication systems would face similar obsolescence problems. A spacecraft designed to communicate using radio frequencies or communication protocols current at the time of launch might arrive at the galactic centre to find that Earth no longer monitors those frequencies or uses completely different communication technologies. The mission's findings might be untransmittable or uninterpretable by the time they could be sent back to Earth. The scientific instruments aboard the spacecraft would reflect the questions and priorities of the era when the mission was launched. Over thousands of years, scientific understanding advances dramatically. Consider how different our scientific questions are today compared to those of scientists 26,000 years ago, which effectively didn't exist in any form we would recognize. The spacecraft would be designed to answer questions that would be considered trivial, misguided, or completely irrelevant by the time it reached its destination. The data formats, computer systems, and analysis methods incorporated into the spacecraft would become increasingly archaic as the mission progressed. Software would be unable to receive updates over such vast distances, meaning that the computational capabilities of the spacecraft would be frozen at early 21st century levels while technology on Earth continued to advance. This technological stagnation would severely limit the spacecraft's ability to adapt to unexpected findings or situations. The information problem extends to the crew of a generation ship as well. The education and training of the original crew would reflect the knowledge available at the time of launch. As this knowledge became increasingly outdated during the journey, each successive generation would be trained using information that had less and less relevance to the actual conditions they would encounter upon reaching the destination. By the time the ship reached the galactic center, the crew's understanding of astronomy, physics, and other relevant fields might be considered primitive or even incorrect by the standards of contemporary Earth science. This knowledge obsolescence creates a fundamental disconnect between the mission as conceived and the mission as executed. A journey planned with the best information available today would be executed in an environment that differed in countless unknown ways from what was expected, using technology that had become obsolete, guided by scientific understanding that had been superseded, and attempting to answer questions that were no longer relevant. Unlike many other challenges of interstellar travel that might potentially be overcome with sufficient technological advancement, the information obsolescence problem stems from the fundamental limitation of light-speed information transfer in our universe. No foreseeable technology can overcome the fact that information about distant regions of space can only travel at the speed of light, creating an unavoidable lag that renders long distance, long-duration missions fundamentally problematic in ways that may have no practical solution. The challenges of outdated information are further complicated by another often overlooked factor in interstellar travel: the complex web of magnetic fields that permeates our galaxy. These invisible but powerful forces create yet another layer of obstacles for any spacecraft attempting to reach the galactic center, with effects that range from navigation interference to direct physical hazards for both equipment and human passengers. Galactic magnetic fields exist on multiple scales throughout the Milky Way. The large-scale field follows the spiral arms of the galaxy, while smaller-scale fields are associated with individual gas clouds, star-forming regions, and other local features. The strength of these fields varies considerably, from just a few microgauss in the galactic halo to hundreds or even thousands of microgauss in dense regions near the galactic center. While these field strengths might seem insignificant compared to the magnets we encounter in daily life, their effects become substantial over the vast distances of interstellar space and during the extended duration of an interstellar journey. A spacecraft traveling through these fields would experience a variety of potentially problematic interactions, particularly if moving at the high velocities necessary for practical interstellar travel. One of the most direct effects would be the interaction between the galactic magnetic fields and any electronic systems aboard the spacecraft. Magnetic fields induce electrical currents in conductive materials moving through them, a basic principle of electromagnetic induction. For a spacecraft traveling at a significant fraction of light speed, even weak magnetic fields could induce substantial currents in its electrical systems, potentially disrupting critical equipment or requiring significant power to shield against. These induced currents would be particularly problematic for sensitive scientific instruments, navigation systems, and communication equipment. Instruments designed to measure external phenomena might be overwhelmed by electromagnetic noise generated by the spacecraft's own movement through the galactic magnetic field. Navigation systems relying on electromagnetic sensors would face similar interference, potentially compromising course calculation and adjustment. The problem becomes significantly worse near the galactic center, where magnetic field strengths increase dramatically. The central few hundred light-years of our galaxy contain magnetic fields estimated to be 50 to 100 times stronger than in our solar neighborhood, organized into complex structures that include loops, filaments, and turbulent regions. A spacecraft entering this environment would encounter rapidly changing magnetic conditions that would be extremely difficult to predict or navigate. The interaction between these magnetic fields and charged particles creates another hazard. Galactic magnetic fields trap and channel charged particles, creating regions of higher radiation density along magnetic field lines. These regions form natural radiation belts similar to Earth's Van Allen belts, but on a vastly larger scale. A spacecraft crossing these structures would encounter increased radiation levels beyond the already dangerous interstellar background. The most intense magnetic structures in our galaxy are associated with specific features near the galactic center, particularly the radiofilaments observed extending perpendicular to the galactic plane. These filaments contain magnetic fields up to 1,000 times stronger than the average galactic field and extend for dozens of light years. Their origins remain poorly understood, but they represent potentially hazardous regions that a spacecraft would need to detect and avoid. Another challenge arises from the interaction between the spacecraft's own magnetic fields and those of the galaxy. Any long-duration spacecraft would likely use powerful magnetic fields for various purposes: radiation shielding, plasma containment for propulsion, or artificial gravity generation. These fields would interact with the galactic magnetic environment in complex ways, potentially creating drag, torque, or instabilities that would affect the spacecraft's trajectory and orientation. For propulsion systems that rely on electromagnetic interactions, such as various proposed plasma or ion drives, galactic magnetic fields could directly interfere with engine operation. These propulsion systems generally require precisely controlled electromagnetic conditions to function properly. External magnetic fields that vary unpredictably could reduce engine efficiency or even cause system failures at critical moments. The effects of magnetic fields on human health add another layer of concern. While the direct effects of static magnetic fields on human biology are generally considered minimal at the strengths found in interstellar space, the long-term consequences of exposure during a multi-generational journey remain unknown. More significantly, the interaction between magnetic fields and charged particles creates secondary radiation effects that could pose additional health risks beyond the direct cosmic ray exposure we've previously discussed. Perhaps the most challenging aspect of galactic magnetic fields is their unpredictability. Our current maps of the galaxy's magnetic structure are extremely crude, showing only large-scale patterns derived from limited observational techniques. The fine details, particularly the small but potentially significant variations that could affect a spacecraft's systems, remain largely unknown. This uncertainty makes it virtually impossible to plan a safe trajectory through the three-dimensional magnetic landscape of our galaxy. Even if we could somehow map the current magnetic structure of the galaxy with perfect precision, these fields change over time. Turbulence in the interstellar medium, supernova explosions, and activity near the galactic center constantly reshape magnetic field lines. Over the thousands of years required for a journey to the galactic center, the magnetic environment would change substantially from whatever was mapped at the mission's outset. The combination of these factors, induction effects, radiation channeling, propulsion interference, potential biological impacts, mapping limitations, and temporal variation creates yet another layer of challenges for interstellar travel that has received relatively little attention in discussions of reaching the galactic center. Unlike some other barriers that might be overcome with sufficiently advanced technology, The pervasive and dynamic nature of galactic magnetic fields represents an environmental factor that any physical spacecraft would need to contend with, regardless of its technological sophistication. Even if we could somehow overcome all the technical challenges posed by galactic magnetic fields and the other barriers we've discussed, we would still face perhaps the most practical obstacle of all: the economic reality of mounting such an expedition. The financial and resource requirements for a mission to the galactic centre would be so astronomical that they render the entire concept economically unfeasible. Regardless of technological capability, to understand the scale of the economic challenge, consider that the International Space Station, a relatively modest orbital facility just 400 kilometres from Earth, cost approximately $150 billion to build and has required billions more annually to maintain. A generation ship capable of sustaining a viable human population for thousands of years would need to be thousands of times larger and more complex than the ISS, with corresponding increases in cost. The sheer material requirements for such a vessel would strain global resources. A conservatively sized generation ship with sufficient radiation shielding, living space, agricultural areas, manufacturing facilities, and propulsion systems would require thousands of tons of specialized materials, advanced alloys, rare earth elements, fissionable materials, superconductors, and countless other resources that are already scarce and expensive on Earth. The cost of lifting these materials to orbit represents another economic barrier: current launch costs. Even with the most efficient systems like those developed by SpaceX, remain around $1,000 to $3,000 per kilogram to low Earth orbit, even assuming dramatic reductions in launch costs through technological advancement. The expense of placing the millions of tons of material required for a generation ship into space would likely exceed the entire global GDP for multiple years. Research and development costs would add another layer of economic burden. Most of the technologies required for long-duration interstellar travel don't currently exist in practical form. Developing reliable life support systems that could function autonomously for thousands of years, propulsion systems capable of reaching a significant fraction of light speed, radiation shielding effective over millennia, and the countless other novel technologies required would necessitate research programs dwarfing anything in human history. The energy requirements for construction and launch represent yet another economic hurdle. Accelerating a massive generation ship to even a small percentage of light speed would require energy equivalent to years or decades of global energy production. Generating, storing, and deploying this much energy would require infrastructure investments that would strain the resources of even the most advanced global economy. The time scale of the project creates additional economic complications. Investment in a project whose returns, if any, would not be realized for tens of thousands of years defies all conventional economic thinking. No government or private entity rationally invests in projects where the payback period exceeds not just the lifetime of the investor, but potentially the lifetime of human civilization as we know it. The opportunity cost of such an enormous investment presents another economic argument against galactic center exploration. The resources required could alternatively be directed towards solving immediate problems on Earth: climate change, disease, poverty, or advancing space exploration in more practical ways, such as establishing permanent bases on the Moon or Mars. The diversion of such vast resources toward a single, speculative mission, with returns so distant in time, would be difficult to justify by any conventional cost-benefit analysis. The economic challenges extend to the operational phase of the mission as well. A generation ship would need to be entirely self-sufficient economically, developing its own internal economy to allocate resources, maintain infrastructure, and provide for the needs of its population over thousands of years, creating a stable economic system that could function independently for such timeframes, without external inputs or corrections, presents social and economic engineering challenges that may be fundamentally unsolvable. The sustainability of the project's funding over its development phase presents yet another barrier. Major space projects on Earth already struggle with funding consistency across different budget cycles, administrations, and economic conditions. A project requiring sustained investment over decades just for development would be vulnerable to shifting political priorities, economic downturns, and competing demands for resources. History shows that even much shorter-term space projects frequently face cancellation or dramatic scope reduction due to funding challenges. Even if we assume unprecedented international cooperation to spread the economic burden, the sheer scale of investment required would still represent a significant fraction of global economic output for years or decades. Such a massive diversion of resources would likely have substantial negative impacts on the global economy, potentially reducing standards of living, limiting other scientific and technological development, and creating political resistance that would threaten the project's viability. The economics of information return create another challenge. Traditional investments expect returns that can benefit the investors or their proximate descendants. The information gathered by a mission to the galactic center would not begin returning to Earth until 26,000 years after launch at minimum. The economic value of scientific information with such a delayed return is effectively zero by any conventional economic calculation. Perhaps the most fundamental economic reality is that space exploration has historically been motivated by either practical returns, such as satellite communications or Earth observation, or by national prestige and competition. A mission to the galactic center offers neither short-term practical benefits nor the prestige element that comes with achievable goals within a human lifetime. Without these motivators, marshalling the economic resources required becomes not just difficult but effectively impossible. The combination of these economic factors, the unprecedented scale of required investment, material constraints, launch costs, research and development needs, energy requirements, irrational timescales for return, opportunity costs, internal economic sustainability challenges, funding sustainability, global economic impacts, and lack of conventional motivators creates an economic barrier that may be even more insurmountable than the technical challenges we've discussed. In a world of finite resources and competing priorities, the economic case for a mission to the galactic center simply cannot be made by any rational calculation. The economic infeasibility of galactic center exploration reveals another sobering reality. Even if we somehow overcame the financial barriers and launched such a mission, the crew would face the absolute certainty that no rescue or support would ever be possible once they departed our solar system. This stark isolation creates safety and psychological challenges that may be the most humanly significant of all the barriers we've discussed. For every space mission conducted to date, contingency plans exist for emergencies. From Apollo 13's famous successful failure to emergency evacuations from the International Space Station, the possibility of rescue has always been a fundamental assumption in human spaceflight. A mission to the galactic center would be the first in human history where rescue would be categorically impossible under any circumstances. This impossibility stems from the same distance and time constraints we've discussed throughout. Any emergency signal sent from a spacecraft, even a few light years from Earth, would take years to arrive, and any response would take equally long to return. For a vessel thousands of light years into its journey, even communication becomes meaningless, let alone physical assistance. The crew would know with absolute certainty that they face any emergency entirely alone. The technical implications of this rescue impossibility are profound. Every system on the spacecraft would require levels of redundancy and reliability far beyond anything previously engineered. Current spacecraft are designed with the understanding that mission-critical failures can result in aborted missions and crew return. A generation ship would need to be designed to handle any conceivable failure without external assistance for thousands of years, a standard of reliability that may be fundamentally unachievable. Medical emergencies present a particularly troubling aspect of this isolation. A generation ship would need to be entirely self-sufficient in medical capabilities, able to handle everything from routine healthcare to major traumas to novel diseases that might evolve during the journey. No outside medical expertise could ever be consulted. No emergency evacuations would be possible, and no new medical supplies could ever be delivered beyond what was initially brought or could be manufactured on board. The lack of external support creates cascading engineering challenges. Without the possibility of resupply, the ship must carry every replacement part it might need over millennia, or have the capacity to manufacture them from raw materials. This significantly increases the initial mass of the vessel, exacerbating the already enormous propulsion challenges. Alternatively, the ship must include complete mining and manufacturing capabilities to produce replacement parts from raw materials, essentially requiring a miniature industrial civilization contained within the vessel. The impossibility of course corrections based on external observations represents another support limitation. Earth-based telescopes might detect a hazard in the spacecraft's path years after departure, but this information would be useless if it couldn't reach the vessel in time. The ship would have to rely entirely on its own sensing systems to detect and respond to dangers, without the benefit of Earth's much larger and more powerful astronomical instruments. Knowledge and skill degradation over generations would normally be addressed through education and training updates from Earth, but the communication delays would render this impossible. The ship's population would have to maintain all critical knowledge internally across generations, with no way to receive updates about new discoveries, technologies, or methodologies developed after their departure. The psychological impact of knowing that no help could ever come would be substantial. Even in the most isolated human environments on Earth, Antarctic research stations, submarines, or remote expeditions, the possibility of emergency evacuation exists. Even if difficult, the absolute knowledge that any problem, no matter how severe, must be solved internally or result in mission failure would create a psychological burden unlike anything in previous human experience. Resource limitations become even more critical without the possibility of resupply. Any miscalculation in the requirements for air, water, food, or other consumables could not be corrected after launch. If critical resources began depleting faster than anticipated, no emergency shipment could ever arrive to prevent disaster. The margins for life support planning would need to be extremely conservative, further increasing the vessel's size and initial resource requirements. Power generation presents similar challenges without external support. Any failure in the ship's power systems would need to be addressed using only onboard resources and expertise. Nuclear power sources would eventually deplete their fuel, while alternative power generation systems would degrade over time. Without external resupply of fuel or replacement components, maintaining adequate power throughout the journey would require levels of system longevity and redundancy that may be technically unachievable. The navigation requirements become even more stringent without external support. Current deep space missions rely on Earth-based tracking stations to precisely determine their position and trajectory. A generation ship would need to perform all navigational calculations internally, with no external verification or correction. Any cumulative errors in navigation could send the vessel drastically off course with no possibility of external guidance to identify or correct the deviation. Perhaps most fundamentally, the impossibility of rescue means that any critical failure becomes an existential threat to the entire mission. There would be no lifeboat, no backup plan, and no possibility of saving even a portion of the crew or mission data through external intervention. This creates a mission profile with zero tolerance for certain categories of failure, a standard that may be fundamentally impossible to meet given the timescales involved and the limitations of human engineering. The combination of these factors, technical isolation, medical self-sufficiency requirements, resupply impossibility, knowledge maintenance challenges, psychological impact, resource limitations, power concerns, navigation independence, and zero failure tolerance creates a support and rescue barrier that may be insurmountable regardless of technological advancement. Human space exploration has always operated within a paradigm where some form of external support or rescue remains at least theoretically possible. A mission to the galactic center would require abandoning this fundamental safety assumption, potentially crossing a line beyond which responsible mission planning cannot proceed. Given all these seemingly insurmountable barriers to physical human exploration of the galactic center, it's worth considering the theoretical alternatives that might allow humanity to achieve similar scientific and exploratory goals without requiring physical travel across these vast distances. These alternatives range from enhanced remote observation to theoretical physics concepts to robotic exploration, each offering potential pathways to knowledge that circumvent many of the limitations we've discussed. The most immediately practical alternative is continued advancement in astronomical observation technologies. Our ability to study the galactic center remotely has improved dramatically in recent decades, with instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and ground-based radio telescope arrays providing increasingly detailed views. Future observatories like the James Webb Space Telescope and others will continue this trend, potentially revealing details about the galactic center that would have required physical travel to discover in previous eras. Interferometry, combining multiple telescopes to function as a single, much larger instrument, offers particularly promising capabilities for remote study of the galactic center. The Event Horizon Telescope, which produced the first image of a black hole in 2019, demonstrated this technique's power. Future space-based interferometer arrays could potentially achieve resolution sufficient to observe details at the galactic center that are currently invisible to our instruments. Robotic exploration represents another alternative that avoids the human-specific challenges of interstellar travel. Advanced probes could potentially be designed with much longer operational lifespans than human-carrying vessels, without requirements for life support, radiation protection for biological organisms, or psychological considerations. While still subject to many of the physical limitations we've discussed, robotic missions could potentially be made much smaller and faster than human missions, improving their feasibility. Miniaturization offers a potential path to overcoming some propulsion challenges. Concepts like Breakthrough Starshot propose using powerful ground-based lasers to accelerate gram-scale probes with light sails to significant fractions of light speed. While such tiny probes couldn't carry humans or even substantial scientific instruments, they could potentially carry basic sensors and communication equipment. Swarms of thousands or millions of such probes might collectively gather significant data about interstellar space and distant targets. Artificial intelligence would be essential to any robotic exploration alternative. Advanced AI systems could potentially operate spacecraft autonomously over the long timescales required, making scientific observations, navigation decisions, and equipment adjustments without human intervention. As AI capabilities continue to advance, the gap between what human explorers and robotic systems can accomplish continues to narrow. Quantum technologies offer several theoretical alternatives to physical travel. Quantum entanglement, while currently not useful for information transfer faster than light, could potentially enable new forms of communication or sensing that we haven't yet discovered. Research into quantum technologies is still in its early stages, and breakthroughs in this field might eventually provide tools for studying distant regions of space in ways we cannot currently envision. Virtual exploration represents another alternative approach. As computational power and simulation capabilities advance, we may eventually be able to create increasingly accurate simulations of the galactic center based on observational data. Scientists could then conduct virtual experiments within these simulations, testing hypotheses without requiring physical presence. While not the same as direct observation, such simulations might answer many scientific questions at a fraction of the cost and risk of physical exploration. Advanced data analysis techniques offer yet another alternative path to knowledge. As our ability to extract information from limited observational data improves through machine learning and other analytical approaches, we may be able to deduce facts about the galactic center that would previously have required direct measurement. The information content of the light and other radiation reaching us from the galactic center is enormously rich. We simply need better tools to fully interpret it. theoretical physics advancement might eventually provide entirely new approaches to the challenge, while concepts like wormholes, warp drives, or other faster-than-light technologies remain firmly in the realm of speculation rather than practical engineering. Continued research into fundamental physics could potentially reveal currently unknown aspects of space-time that might enable new approaches to interstellar exploration or observation. A more speculative but intriguing alternative involves the potential for post-human evolution or development. If humanity eventually develops the capability to transfer consciousness to non-biological substrates or otherwise transcend our current biological limitations, many of the challenges we've discussed, radiation exposure, period, lifespans, life support requirements, might become irrelevant. Such a radically transformed humanity might approach galactic exploration in ways we cannot currently imagine. The search for extraterrestrial intelligence, SETI, offers another alternative approach. If technologically advanced civilizations exist elsewhere in the galaxy, they might have already studied the galactic center and might be willing to share their knowledge. While highly speculative, the possibility of learning from more advanced civilizations cannot be entirely dismissed as a potential shortcut to knowledge about regions of our galaxy that remain physically inaccessible to us. Regardless of which alternatives ultimately prove most fruitful, the fundamental message is that physical human exploration is not the only path to knowledge and discovery. Throughout history, humanity has demonstrated remarkable ingenuity in finding alternative approaches when direct routes prove impossible. The barriers to physical exploration of the galactic center may be insurmountable, but human curiosity and creativity will likely find other ways to satisfy our desire to understand this mysterious and fascinating region at the heart of our galactic home.